So welcome all the brave people who survived over 6 lectures. Right, this is also statistics and error bars. So this is your feedback from previous 5 talks. How useful the talk was, how easy, interesting, your own knowledge, how much you learned and how much you understood. So they are all scaled to the same scale. Each point is the mean, and error bar is a 95% confidence interval. So you now know exactly what these are. So that's quite interesting to see that. Well, you find it usually useful. It was kind of going down, but the last talk about error bars, where there were no equations at all, you found it more useful and much easier. And of course, you understand it also much better. When I was talking about confidence intervals, it was just going down and down. It was getting more. Your knowledge, I mean, error bars are huge, so there is no really statistical difference. But there is some sort of a trend here of your knowledge going up. And actually, it might be a selection effect because there is just fewer and fewer people. So this is just a hardcore, but people who are interested in statistics. So yeah, you may be, and you learned roughly the same every time. Yeah, I will see what happens after this talk. Oh, by the way, there is still probably some of them left. So can you pass it around? I appreciate this. Right. So previously, I talked to you about error bars and how to make good graphs and plots. So I mentioned that clarity of presentation, of course, that's what you aim at. You need some good lines, symbols, clear labels. Don't forget labels. And you can use logarithmic plots. Box plots are a good alternative for standard deviation. They show distribution of data in a non-parametric way. They are very nice. Bar plots, sometimes they are useful, but you have to be careful to show only additive quantities. The baseline here has to be at 0, and never use bar plots in logarithmic space. Be careful when this variable is continuous, and always show upper and lower error bar, never this one. I also mentioned significant figures and how to quote numbers and errors. The quick rule is that you quote only significant figures, and you use arrow in the arrow to find how many significant figures you have in your arrow, and then align it at the same decimal place with the number and quote only this. Right, let's start with an example for today. So imagine an experiment where you measure position under a microscope of 2 fluorescent dots, and you have X, Y, and Z coordinates of these 2 dots. This is in micrometers. There are some numbers, okay? And you know from your microscope that each of them these numbers have some errors, uncertainties. And uncertainty in XY plane is about 120 nanometers. Uncertainty in Z direction is different. It's about 200 nanometers. So basically, these 4 numbers have this error, and these 2 numbers have this larger error. Now, if you were to find distance between these 2 dots, you can use this very simple formula. And you can put all these numbers here, and you get 1.62 micrometers. Okay, that's fine. But there are errors here. So obviously, this number is also uncertain because there are measurement errors here. So you have to somehow find error of R. And how would you do this? Well, you need to propagate errors from X, Y, and Z. And this is the topic of the first part of a talk about error propagation. And I will start with a quote from John von Neumann. If people do not believe that mathematics is simple, it is only because they do not realize how complicated life is. And that comes from John von Neumann, a man who was a brilliant mathematician, very, very scarily brilliant. One of his lecturers, when he was at university in Zurich, he was doing a seminar for advanced students. And he presented a theorem in maths and said, okay, we don't know proof of this theorem, and possibly it's very difficult to prove it. No one has done it so far. And about 5 minutes later, when he was doing this, von Neumann just raised his hand and said, I can prove it. And he went to the blackboard and just wrote down proof. And this lecturer, he said, well, after that, I was afraid of von Neumann. So yeah, funny man. Yeah, he also, what else did he say? There was something funny, which now I forgot, but never mind. Right, so how many of you know something about derivatives. Are you familiar with the concept of a derivative? I know it's a silly question, but who is familiar with derivatives? Who can calculate derivatives, actually? Okay, right. So obviously, this is a topic for another lecture series, basically, to explain everything. So I will do a crash course in 2 minutes of derivatives, so this might not work. But so consider a function y, which is f of x, and it's presented here. So this is x, this is y, and this is a function f. It can be anything. I will show you some examples in a moment. So derivative is basically the rate of change of this function. It's change in y divided by change in x. So you have change in x, so you go from here to there, and there is a corresponding change in y. And it works only for small delta y and delta x. So derivative is basically slope of this curve. If you draw a tangent line, and the tangent of this angle theta is basically the derivative of x in this particular point. So the steeper the curve, the higher the derivative, the more flat the curve here, the derivative would be lower. This is just an approximation. The actual formula, you do it as a limit when delta x approaches 0 of this thing. So, but for a moment, all you need to know that derivative is basically slope of the curve. And that's what we are going to use. Now, these are a few derivatives of functions. You can calculate these things analytically, and I'll just show you a few examples, which I'm going to use later in the talk. So if you calculate derivative of a very simple function, this is our function f. It's a times x, where a is a constant. So when you take derivative, you get a. Derivative of x to a power r, where r is a constant, is r times x to power r minus 1. It's a simple formula. And there are two examples here. If you have x squared, the derivative would be 2x. And if you have 1 over x is x to minus 1. So using this formula, it will be minus 1 times x to the power minus 2, which is minus x over 1 over x squared. So I will use this very soon, so remember this one. And a derivative of a logarithm with base a is 1 over x times natural logarithm of a. And you can continue like this. Lots of elementary functions you can calculate derivatives very, very simple. Okay. So how do we propagate errors? So let's start with, well, again, we have a certain function. So consider a quantity x with error delta x, and this is something we start with. So we have a measurement, like in this initial example. You have a position of a fluorescent dot and a certain error. And we now transform this variable into a new variable, let's call it y, via this function f of x, and it might look this way, for example. And this function f could be a constant, could be a logarithm, could be a square root, or whatever. Now, what we aim to find is to find error of this quantity y. So given x plus minus delta x, we want to find y plus minus delta y. And if you look at this plot, there is one thing immediately obvious, that for the same delta x, for the same error in x, depending on how steep this function is, you can have corresponding error in y, which is small, because function here is flat, so large variability in x will cause only small variability in y, and vice versa. When the function, this transformation function, if it is steep like this, then the same variability in x will cause much higher variation in y. So you can immediately see how intuitively how it works and where we take it to. So basically, if these errors are small and function is approximately linear here, we can say that the delta y divided by delta x is roughly a derivative of this function at this point, which is very useful, because we can rewrite it this way. We can write that delta y is df by dx times delta x, and this is the derivative, df by dx. I put an absolute number here because df by dx, depending whether a function goes up or down, it can be either positive or negative, but our errors are always positive. It doesn't matter whether error is from here to there or the other way around when the function is going down. So there is an absolute value. An alternative way of writing this down, and we'll come back to this later, when we look at multiple variables, is basically taking a square of everything, and delta y squared is the derivative squared times delta x squared. So it's a very simple formula for propagating errors. And let's see how it works in practice. So I write it down again here. Right. Let's consider scaling. So you have a variable, an error, and you want to scale it by factor 10, for example. So what do? Our function is a times x, where a is a scaling constant. So we use this formula. Derivative, as I showed you a moment ago, of ax is simply a, and it will be an absolute value of a, as shown here, times delta x. So this is our final transformation. If a variable is scaled, then its error is scaled in the same way. So if you have, for example, scaling by factor 10, if your measurement is 5 plus minus 3, then your scaled number will be 50 plus minus 30 because you scale them by the same thing. It's very simple. A little bit more complicated when you use a logarithm. So let's take logarithm with base 2. That's our transformation. We use the same formula. Derivative of the logarithm I showed you a moment ago is 1 over x natural logarithm of a. So that would be 1 over x times natural logarithm of 2, because this is our base, times delta x. And this number, 1 over log 2, is about 1.44. This is an approximate formula. And as you can see, I removed absolute value from here, from this formula. Why did I do this? Say again? It's x is positive. X has to be positive, because otherwise we won't be able to take the logarithm. So in the first place, it is always a positive number, so we don't need absolute values here. So it's 1.44 times delta x over x. And this is something which is worth remembering, because in biology we quite often transform variables from linear scale to logarithmic scale. And when you have errors, you have to transform them. And you can do it this way. And this is an example. If your x is 4 plus minus 0.5, then your transform variable will be log base 2 of 4 is 2, and delta x over x, it's 1/8 times 1.44 is about 0.2. So this is the transform variable with its error. And error here, it could be anything, because it affects transformation of any type of error. So it could be standard error, it could be a confidence interval. You can also transform standard deviations in the same way. We stay with logarithms for another slide. So if you have a transformation, let's say I use log 10 now. So this formula looks a little bit different. There is, instead of log 2, is log 10 here, and the constant will be about 0.43 delta x over x. Now imagine that you have several data points, 30 in this case, with error bars. And quite often in measurements, it happens that you have error which is proportional to the variable that you measure. So if variable is small, the error is small. If variable is big, its error is also much bigger. And this is an example where error is actually proportional to x, to its variable. So here x is small and its error is small. Here x is bigger and its error is also bigger. And this is in linear scale. Now if you calculate logarithms, the error of the log is a constant times delta x over x. But because error is proportional to its variable to x, then this quantity is constant. So in logarithmic spells, your errors are all constant. So you see they are smaller and larger here, but this error and this error in log space is basically the same. So this is a property you might see in your data from time to time, depending how data are distributed. If data are distributed log normally, this is rather typical.
Why are they symmetrical in top graph? At the error bars? In the top one there.
In the top one? Why? Well, they are symmetrical. That's what I assumed here, that this is x plus minus delta x.
And they stay symmetrical?
Yeah, in a sense, because this is an approximation. When you do error transformation, you assumed that your transforming function is locally linear, and error also transforms as symmetric. This is not exact calculation. You could probably calculate the lower bound and upper bound and find logarithms of them, which is a little bit more complicated. But if you want to estimate your errors, they will remain symmetrical. This is approximation only. Now, if we go to many variables, so if you have variables x1, x2, up to xn, And what is very important, these variables are independent. I will come back to this later. So you have not correlated independent variables, n of them, and each of them has arrow, delta x1, delta x2, up to delta n. You calculate new variable, just one, as a function of all these variables. This is the formula we are going to use for arrow transformation. I will not show you a derivation of this. It's a little bit more complicated. But the formula is very similar to what you saw a moment before. It's a derivative with respect to x1, and this is a partial derivative, which means it's a derivative in one particular direction. So if you have more variables, you consider, so if you calculate partial derivative with respect to x1, you think for a moment that all other variables, x2 up to xn, they are constant, they are fixed, and you look in just one direction and calculate derivative. But the rules for calculating derivatives are exactly the same. So this is derivative squared and times arrow squared. The second derivative squared times arrow squared, and so on. It's the sum of all these derivatives and arrows. So it's pretty straightforward formula. And we can see how it works. So imagine that you calculate now a sum of two numbers, x1 and x2. That works exactly the same for difference. So we apply this formula for two variables, derivative with respect to the first variable squared times its arrow squared, and the same for the second one. Derivative of this, a partial derivative with respect to x1, is simply 1. You consider this as a constant, so it's 0, and derivative of this is 1, the same as of the second one. So these derivatives, this is 1, this is 1, all you have left is just arrows squared. So arrows add in quadrature when you add or subtract two numbers. And there is a simple geometrical interpretation of this. You can draw a triangle like this. And this is arrow in the first variable, this is the arrow in the second variable, this is the arrow in y in the resulting variable, just straight away from this formula. So you can imagine what it looks like if, for example, this arrow, if one arrow is much, much smaller than the other one. Imagine that this triangle is very, very narrow, and then delta y would be basically the same as delta x1. So if one arrow is negligible, then the other one just propagates straight. And this is another example. The first variable, 8 plus minus 3. The second variable, 10 plus minus 4. You add this together, it's 18. And 3 squared plus 4 squared, it's 9, plus 16 is 25. Square root of this is 5, 18 plus minus 5. A very simple rule, very simple equation for adding variables. Now, if you want to apply a similar formula for a ratio, a product, I would do it for a ratio. It gets a little bit more complicated, but it's still straightforward calculations. So we use this formula. Derivatives, partial derivative, df by dx1, you consider this as a constant, so it's simply 1 over x2. df by dx2, it's x1 as a constant, and 1 over x2, I showed you, is minus 1 over x squared. That's the derivative. And we put them in here. So that's the first derivative, that's the second derivative times arrows. It's quite simple. Now I do some reshuffling here to reveal some symmetry in this equation. It will help us later. So what I did here in this first term, I multiplied and divided it by x1 squared. I need x1 to be different, to be not equal 0. And what you see if you do this, and I also extracted this x2 squared is under this squared, so I extracted it here and divided between this and this. So it's x1 over x2 and delta x2 over x2. And what you see here is the ratio of x1 over x2 squared times fractional error, and again the same ratio times another squared error. So we can take it out of a bracket, simplify it, and of course x1 over x2 is y. So there is y squared times the sum of fractional errors squared. So again, this formula is actually quite simple. For a ratio like this, the errors add the fractional errors. This is a fractional error, this is fractional error. They add in quadrature in a very similar way. So our geometrical interpretation would be fractional error on x1, fractional error on x2, and this is fractional error on the result. So it's easy to remember these things. And if you look at another example, 25 plus minus 2.5, 10 plus minus 1. So as you can see, these are 10% errors in x1 and x2. And if you calculate this, the ratio will be 2.5 plus minus 0.4. So 10% error in these variables will give you a 14% error in the result. Well, that's very simple from the triangle because it's a square root of 2. If you have 1 and 1 here, or 0.1 and 0.1 here, it will give you 0.14. Right, I hope it is not too complicated. The equations are pretty straightforward, I hope. All right. If we come back to our example from the beginning of the talk, so we have two fluorescent dots, and we have positions, x1, y1, z1, and x2, y2, z2. The numbers are here. Arrows, and we find distance between them. Now, I can use these propagation equations if you see that r is a function of 6 variables. So it's not 1, it's not 2, it's 6. It's a little bit more complicated. So you have to use this full formula. Actually, it's simpler than it looks like. You have a derivative by x1, dr by dx1, times error of x1. And error of x1 is the same as error of y1, x2, and y2. This is just one error. So it's this delta xy squared. And then the second variable, this is y1, error is the same. And the third variable is z1, and error is delta z. So this is the first row is for the first dot, and the second row is exactly the same, but it's for the second dot. So there are 6 terms here. Each of them consists of a derivative and error squared. And if you take this equation and calculate all the derivatives, it's not very complicated, and I suggest this as a homework. You can do it yourself. And then you can prove that at the end you will get this equation. So this is the equation if you measure distance between 2 dots under a microscope, and I believe some of you do it from time to time. And if you have measurement errors, you need to find error on this distance as well. And if you do this, if you apply this formula, this is what you get. The result will be 1.6 plus minus 0.3 micrometers. So if you want to publish this result, you really need this error and you need this formula. Now, error propagation is useful in some cases and not very useful in others. I will show you a case to compare these two cases, and you can decide which one is more useful. So consider an experiment where you measure IC50 of a drug. An experiment is done in 5 replicates. And these are your measurements in nanomolars. So there are 5 numbers here. Now, an alternative way of presenting IC50 is taking a logarithm of this, or rather a minus logarithm, and you take your IC50 divided by this by 1 molar, and you get a number. This is quite commonly used. And this is done because IC50 is typically log normally distributed, so these numbers, they make much more sense. And they are presented here, 7.6, 7.2, and so on and so forth. So if you have 5 replicates and you want to find the mean and its error, you can do it in 2 ways if you want to find it for p, for the logarithmic version. You can either calculate errors on this and propagate them using a logarithm, the logarithmic formula, or you can do a direct calculation. And this is the actual calculation. There are just a few numbers here. So the mean out of these 5 measurements is 54.6 nanomolar. Standard error is 18.2. I would just focus on standard errors for a moment. But you can do the same for confidence intervals. So there are 5 replicates. So as you remember from previous talk, there would be only one significant figure in the error. So instead of 18.2, this is just 20. And then you align error and number at the same decimal place and cut off non-significant numbers. So the result, to quote, will be 50 plus minus 20 nanomolar. This is our result. And then we can calculate PIC50 by taking a logarithm of this number and divided by 1 nanomolar. This is 7.26. Now, error propagation is here. So this is the formula for log base 10, which is 0.43 times error divided by the number. Error is here, number is here. If you do this, you will get about 0.14. And again, one significant figure in the error. So finally, you write this down as 7.3 plus minus 0.1. Obviously, because you have logarithms of these numbers, you can just take these and calculate mean and standard error directly. Mean is this one, standard error is this one. So if you calculate it, you had a slightly different number. It's 7.4 plus minus 0.2. Now, which method is better and why? Any ideas? Well, first of all, if you look at this number, before even we get to errors, the PIC50 calculated by this method is 7.26. Using this method is 7.39. There are two different numbers. It's because here we calculate mean first and then take a logarithm. Here we calculate logarithm first and take the mean. And log of the mean is not the mean of the logarithm. These are two different numbers. It might be debatable which one is better to use. It depends on how your data are distributed. And in this case, as I said, IC50 are distributed log normally, typically. So it's always better to take logarithms of your data and then do calculations, because they will be roughly Gaussian, will be roughly normally distributed. So I would say that this number is probably better to represent your mean. As to the error, well, errors are quite large, as you can see. They're about 30% or so. So the error propagation formula does not work so well. It's only very, very approximate. So it's also better to calculate error this way. So if you have a situation like this where you can calculate your transformed data directly from each replicate, it's always better to calculate errors at the end instead of propagating them. But this is not always possible. That's why I'm showing you how to propagate errors. Right, to summarize this part of the talk, so when a quantity is transformed, its error has to be propagated. When you have a single variable and transformation through a function f of x, you just calculate derivative of this function and multiply by error. This is a very simple way of transforming variables. If you have multiple variables, you use a little bit more complicated formula, which is actually similar to this one, but there is a series of these terms. Each of them is a derivative squared times error squared. And you can use this and that directly. I will leave you this in your handouts. You can download this. These are examples for different transformation functions, how to transform errors so you don't have to calculate all these derivatives. But obviously, in more complicated cases, as the one I showed with fluorescent dots, well, you probably need to do it yourself. Right. The second part of the talk is about linear regression and its errors. It's another funny quote from, I'm not quite sure. It was in a PhD thesis of this blog. It is proven that the celebration of birthdays is healthy. Statistics show that those people who celebrate the most birthdays become the oldest. It's an obvious correlation, which doesn't mean causation. So what is regression? What is a linear regression? Well, regression is a way of finding relationship between two or more variables. And I will focus here in this talk on a very simple linear regression. There are only two variables, and a relationship between these variables is strictly linear, is ax plus b, where a is the slope, b is the intercept. And in this case, usually we use these terms. So x, this here, is called explanatory variable, and y is, on the y-axis, is the response variable. So a and b, if you calculate them from a sample, these are statistical estimators. What do they estimate? Well, they estimate true quantities from the population, which will be the true slope alpha and true intercept beta. And the population would have this regression line, which will give you the mean response to x. So what is the mean response? This is an example from a Hong Kong growth survey. I think I showed you one example before from these data. There are 25,000 adolescent youths, and for each of them we have their height and a mass, body weight. So I plotted mass versus height squared here. If you know body mass index, it's usually, you expect a linear relation between mass and height squared. And indeed, there is a linear relation here. Data are quite scattered, these gray points, but the relation is pretty good. This is the best regression line to entire population from this survey. And I calculated this approximate mean response. So what I did here, I binned data into the bins, each of them containing if I remember correctly, 30 points. So there is a 30 points, 30 data points of this bin, and I calculate mean for them, and so on and so forth. And this is approximation of the mean response. So the mean response is if you take a very narrow range of your explanatory variable and then find in the population, or people in this case, with a given height and measure their weight, and so it will be sort of a slice through this cloud of points here, the mean weight would be here. And it happens that the mean response really follows the straight line very nicely. So that's an interesting thing, that the mean response is very exact. There is some simple underlying relation between x and y here, plus noise, and noise makes these points scattered. But the underlying relation is there, and it's very simple, and it's quite often in biology that you see this simple underlying relation plus quite often huge noise. So these data might be badly affected by noise. Now, how can we use this? So let's have a look at a sample now, not a population, but a sample. And there is an example. There is a random selection of 16 points from the Hong Kong survey, and they are here. Again, I plot mass versus height squared. And this is the best fitting regression line, AX plus B. So this time, the actual response for each point is, for point I, would be AXI plus B plus some additional term RI. We call them residuals. So residuals are plotted here with gray lines. Residual is basically a diversion, how far you are from the best regression line. Sorry. And the way of finding the best fitting line is to minimize this thing, minimize the sum of squared residuals. You want this line to be somewhere in the middle between this point, and you can get it by minimizing this thing, and you do it by finding derivatives with respect to A and B and requesting that they are both 0. This is, again, fairly straightforward process, and if you do this, this is the result. You can find A and B expressed by all these functions M and S. So M is actually the mean. Mx is simply the mean of all x's, so if you calculate the mean of all x's, it's here. And my is the mean of all y's. And this is the point, mean x and mean y. It's right in the middle. And these quantities sxx, syy, sxy are just sum of squared differences between variables and means. And this is the mixed term. So if you calculate all of this from your data, you can find A and B. And these are equations for linear regression. An interesting property of the regression line is it always goes through this middle point, mx, my. So if you plot your data, before you find regression, if you plot or even guess where your centroid of data is, you know that your regression line will go straight through the centroid. Now, before we try, so what we want to find, this is obvious, and you can find it in a textbook, but now we want to find errors on A and B, because this talk is about errors. So before I go there, I need to do some analogy with standard deviation. So if you have a sample of points, let's call them yi, they are scattered around the mean. So there are 12 data points here. This is the mean, and there are residuals showing you how points are scattered around the mean. And I will call them residuals. And residual is the actual data point minus the mean. And standard deviation is basically almost the mean square residual. We use n-1 because there is n-1 degrees of freedom. We lost 1 degree of freedom here to calculate the mean. And that's one of the reasons. The other one is about unbiased estimators, which I told you a few weeks ago. So this is the mean squared residual. Now, if we do regression line, we have a very similar situation. There is a line. These are our data points, and they are scattered. But this time, they are scattered not around the mean, but they are scattered about an inclined regression line. And again, we have residuals. And the residual is the actual data point minus the value of our model here, of our straight line. And we can do a very similar thing. We can find the sum of squared residuals. This time, under square root, we divided by n-2. We lost 2 degrees of freedom to calculate A and B. So this is a direct analogy. So standard deviation will tell you how your points are scattered around the mean. And this standard deviation R, SDR, it's also a standard deviation, will tell you how points are scattered around the straight regression line. If they follow the line very tightly, this SDR will be small. If they are scattered widely around it, this SDR will be high. So this is the measure of scatter. So we can quantify scatter around the regression line using this quantity SDR. And now there is a crucial point here. This is important for over calculations now. Now we assume that the scatter is due to uncertainty in Y only. And this is the basic, very fundamental property of regression. Regression is asymmetric. You take regression from X into Y. There is explanatory and response variable. If you do regression the other way around, you will get a different result. So we assume that these points on X-axis, they are measured precisely. There is no error on them. And overscatter in data points is due to errors in Y, and they are shown here. So we don't know these errors because normally we have just naked points, naked measurements with no errors. So we can use this SDR, the scatter, the measure of scatter around the line, as a guessed error, as an error estimate for each Y. So what I plotted here, each Y has an error delta Y, which is the same for all data points, and it's SDR. This is our guessed error of each Y, and it estimates basically a typical error in the response. Okay. And now, since we know errors on Y, we can use our error propagation equations. We can write down explicitly that A and B, these are our slope and intercept, they are functions of x1, x2 up to xn, y1 up to yn. This is because in these equations, you remember these terms S and M, they contain over x's and over y's. So we can assume that A and B are functions of these variables. And now, variables from x1 to xn, these errors are zero, as I told you. This is the fundamental assumption of a regression. These are assumed to be measured accurately. And then y1 up to yn, they all have the same error as dr. This is our guessed error on y. So we have errors on some of the variables, and we can propagate them to errors of A and B. And we use our known, what I showed you before, equations for error propagation. It is the sum of derivatives squared times errors squared. If you take these equations plus all the explicit equations for S and M, and you put them here and do some straightforward calculations, it probably takes about 10 minutes, you can find these equations directly. So this is the error of A, and this is the error of B. Now you must ask, what are these? I mean, there are delta A and delta B. What do they really mean, these errors? Well, so they represent the width of sampling distributions. We are coming back a few lectures when I explain you the sampling distribution. And if you remember, I showed you an example for the sample mean. So you have a population, you take a sample of, let's say, 5 points, you find the mean. You do it again and again and again. This is this Gedanken, the thought experiment. And you can build distribution of the sample mean, which is called sampling distribution of the mean. And the width of this distribution, the standard deviation of this distribution was what? Do you remember what was it? Standard deviation of the sampling distribution of the mean. What is it? It's complicated. Width of this distribution. Which error is it? Can't hear you. Standard error, yes? This is what you said? Yeah. So if you take the sampling distribution of any parameter, the width of this is the standard error of this parameter. Yeah? I told you this a few times before. You should remember by now. So in this case, it's exactly the same in this case. This is a sampling distribution of the slope. So what I did here, I took all the data, and I took 100,000 samples, which were randomly drawn from the Hong Kong survey, of different size, 16, 30, and 100. And I plot distribution of these slopes. So for each sample, I calculate the regression line and calculate slope and intercept. And this is the distribution of the slope. So the mean slope is somewhere here, and it's distributed around it. And the width of this distribution is the standard error of the slope. And this is what we found here in these calculations. This error is the standard, is the width of this distribution. So these equations from the previous slide here, they are actually standard errors. This is the equation for standard error of the slope. This is the equation for the standard error of the intercept. And then we do a t-distribution approximation, and we can find confidence intervals exactly the same way as we did it for the mean. So we multiply standard error by this critical value t star from t-distribution with n-2 degrees of freedom, and the confidence interval is between a minus t star SE and a plus t star SE, and the same is for B. So these are equations. This is sort of a prescription how to calculate errors on confidence intervals on slope and intercept. I can show you an example. Sorry about that. You can read it later carefully when you take your handouts. This is an example. So these data points, these are the actual numbers. If you want to type them into Excel or whatever and do calculations, you will get the same result. And these are all the equations I showed you. So starting from definitions of M, S, the equations for A and B, standard error, sorry, that's the standard deviation of R and standard errors. And if you do all these calculations, this is what you find. It's just a few numbers, going through a few numbers. I just point you to a few things here. So first of all, this is A and B, slope and intercept. This is the error, this guessed error of Y, which I plotted before. It's about 5 kilograms. So just because of the scatter of these points, we decide that the error on Y is about plus minus 5 kilograms. And the confidence intervals finally calculated are here. So the slope is 27 plus minus 16 kilograms per square meter, but look at the intercept. It's minus 22 plus minus 47 kilograms. So the error on the intercept is huge. It's twice as big as the number itself. Now you might ask, why is it so? So if you look carefully here at the range, that's 2.8, 2.6, maybe 2.5, up to 3 point something. So 0 in this diagram would be probably outside the slide, somewhere here, somewhere down there. So if you vary this point a little bit, your best fitting line would pivot around this point, would go up and down. And the long tail of this line will go up and down very much. So this is your intercept here. So if your data are clustered rather tightly, if it doesn't span a large range, then your intercept will be very poorly estimated. And probably in this case, it would be better to assume that intercept is 0 and then do your calculations again and find error on A only. Okay, the last thing I wanted to show you is the linear fit prediction errors. So I showed you how to find A and B, slope and intercept, and their errors. But then you have regression line Y, okay, which is this, AX plus B. Now, can you find uncertainty on Y directly? So what's the uncertainty of our prediction? And yes, we can do it. So as you notice, Y, this is a function of A and B. And we already found errors on A and B. So we can propagate them like this. Yes, we can use this formula. Except that this is wrong. Now, can anyone tell me why? Can anyone guess what's wrong? I told you something very important when I showed this formula at the top of the slide. What's the very important assumption here about all these variables? They have to be independent. And slope and intercept are not independent. This is our Hong Kong server again. So I took 1,000 random samples of size 16 and calculated slope and intercept for each of them. This is slope, this is intercept. They are very highly correlated. This is because you change your slope and your intercept. So if your slope goes up, your intercept will go down here and vice versa. It's just this pivoting line. So they are very highly correlated. And this formula I showed you, it doesn't work if variables are correlated. When variables are correlated, you have to use a little bit more complicated equation with covariance term in the middle. And of course, I will skip over calculations. This time they are much more complicated. But if you take this formula and calculate your result, this is what you get. And this is something you might use in practice. So this is the standard error of y, of your best fitting line. And you can use the same formula as before. You can use t-distribution to find 95% confidence intervals with using this. So you just multiply it by t star. And this is the result, which you can just see here. This is our best fitting line. And this curve here, this graph curve, is best fitting line plus 95% confidence interval, and then here is minus. So our best fit lies somewhere in this region. It could be this line, but it can go like this, or it can go like that. So this is something you can find fairly easily and calculate it yourself. Right? So, to summarize, a simple linear regression is ax plus b. It's just a relation between two variables. We find best fitting parameters using these equations. An assumption which is here, which is very important, that x is measured accurately and scatter of points around the line is caused by error in y. And we then guess common error in y, which is expressed by this formula as dy r, which is the standard deviation of the residual. And standard error of the slope and intercept then can be propagated from this, and these are equations when you calculate it. Confidence intervals are t star times standard error for n-2 degrees of freedom, and standard error of y can be then propagated from these things. So we start from here, do one propagation of errors, then we do another propagation of errors, and we can find standard error of your best fitting line, and confidence interval is again t star times this standard error for n-2 degrees of freedom. And that's all. That's the end of all our 6 talks. Yeah, thank you for attending. You are the last survivals from the big crowd on the first day. All right, and thank you very much.